Last time we were talking about the mole-to-mole ratio and how we can compare the amount of molecules or group together the amount of moles of my reactants to give me an expectation of how many moles or molecules of my product I can expect. This relationship works both ways. If I know or want a set amount of product, I can set up the amount of reactants accordingly. Now, we were looking at the definition. I wanted to do a quick example to just show you a little bit about how it works. Here we have this reaction. This is a combustion reaction. We have a hydrocarbon molecule in the presence of oxygen, both of them in gas phase, gives me carbon monoxide in gas phase and steam or water in the gas phase. Now, the question is, using the balanced chemical equation, how many moles of carbon monoxide are produced from 3.5 moles of ethane, this fuel molecule right here? So, for that, we need to compare the mole ratio. How many of one allow me to get how many of the other and vice versa. So, this little number on the side is the key to understanding or to obtaining that information. So, for every 2 moles of ethane, I will be able to produce 4 moles of carbon monoxide. That in itself is actually a conversion factor. So I would have a starting quantity and a conversion factor, 2 to 4 or 4 to 2, whatever is convenient for me in this case. You can write them up just like in every other conversion in any of these two, because what we want is the amount of carbon monoxide, then the one to the right is going to be the one that we choose because it has what we want on top, what we want to get rid of in the bottom. So we set it up just like every other conversion. My starting quantity of ethane, my mole ratio, as you can see the units are cancelled, leaving me with this answer, 7 moles of carbon monoxide. Eventually, that number of moles, we might want to change that into grams, simply because that is the amount or the unit that we can use whenever we're working in a lab setting. We don't have scales for measuring moles, but we do have scales for measuring grams or milligrams. And this is actually the, let's say, the scheme that you see right here is the entire scheme that we're going to be working with, or most of the scheme that we're going to be working with relating reactants to products. Reactants, you always start off with a set amount. You have to change it to moles, to then relate to moles of product, and lastly, moles of product to grams of product. We're almost there. We're missing that first step, but we don't need to invoke that first step because our reactants are in the form of moles. So we have this reaction, oxygen turning into ozone. We have 9 moles of oxygen. We want to figure out how many, not moles, how many grams of ozone we are able to produce. So we're doing a 2-step process. First, we're going from moles of reactants to moles of products, and for that we use these little numbers on the side, these stoichiometric factors. And after that, we then do our second conversion, which is moles of ozone into grams of ozone. For that, we're going to need the molar mass of ozone, which is 3 times the molar mass of oxygen that we see on the periodic table. For our first step, our 3 to 2 or 2 to 3 conversion, because we want to keep ozone O3, we're going to be using this one. O3 is on the top, the one that we want to keep. The one that we want to get rid of goes on the bottom. Once I have that, I use my second conversion factor, which is the mole to gram ratio or the molar mass. I set it up in such a way. Now, there's more than one way that we can solve this. You can do it in a single step, like the one shown here, or you can do it step by step. If you're unfamiliar or you're not very comfortable in doing many steps at once, like myself, I do it one step at a time. So I solve this part first. After I'm done with this, then I go ahead and do this part. So 9 times 2/3, 2 over 3. And then whatever I get, I multiply by 48, and that is the amount of grams of ozone that you're able to obtain. Now here, we actually have something that takes us one step further. We start off with a reaction. We have ethanol formed from ethylene and water. We have the chemical reaction right here. And we have amounts of ethylene. We want to figure out amount of ethanol, both in grams. Remember that No matter what, you cannot compare grams to grams for any two species in a chemical reaction. So what we would be doing, we start here. This is going to be our first step right here. We need to change those grams into moles. That gram into moles, we use the molar mass. Again, looking at the numbers of the atomic masses in the periodic table, putting them together, that gets me here. Once I have the moles of those reactants, I can figure out the moles of products that I'm able to get by using the mole ratio or mole-to-mole conversion, those little numbers on the sides. And lastly, once I have the number of moles of my products, it's just a matter of going back and changing it to grams back again. Remember that we cannot do this. It doesn't work. And this is what it looks like. And again, if you're not comfortable doing everything in one step, you can go ahead and break it down into smaller steps. So I would do this part first. Once I do this, 14 divided by 28.05, whatever I get, I change into moles of my product. Lastly, I will go ahead and change it into grams of my product. So it will be a three-step process. I know it's a little bit slower, but it's more systematic. There's less memorization involved and less room for error. And then finally your answer, 20 grams of ethanol. Now with this, there's a few things that we can discuss when it comes to having a reaction on paper versus having it in real life. One of them is what we call the percent yield. The percent yield basically tells us how efficient we were as scientists generating a product. So on paper it says that we can form a set amount of grams, but in reality that number will seldom be the same. So we compare what we actually obtained, or what we call the actual yield, from what we should have obtained on paper, or what we call the theoretical yield. Usually the actual yield is less than the theoretical yield. And that looks like this. Because you usually want it in percentage, we take the actual yield and we divide it by the theoretical yield. So what we obtained versus what we should have obtained on paper. Now, very important guys, actual yield is an experimental measurement. It's not something you can just calculate without any data or any context. So it has to be given to you, unless everything else is given, and then it becomes an algebra type problem. Usually the actual yield is determined in the lab, the theoretical is determined on paper. And lastly, we multiply by 100 to get it in percentage. So in this case, we have ethylene with water to form ethanol, in our previous example. Supposedly it was meant to form 23 grams, but when we did the experiment, we only ended up with 15 grams. So what was the actual yield? Well, I grabbed my actual yield, I divided over my theoretical yield, and I multiplied by 100, so I was 65% efficient. If I'm being honest, that is not such a bad number. In the lab, we usually don't go beyond 80% yield, simply because there's many factors, impurities, changes in temperature, so many variables that the actual yield is usually a little bit far from the theoretical yield. Now, one other concept that we want to go over whenever we're working with this type of reactions is the concept of the limiting reactant. Now, the limiting reactant is the one that gets consumed first. It's the one that will tell you how much are you actually able to form, what is the maximum amount you can form physically. Take a look at the example. I know it looks simple, but it's actually a very good example at illustrating the point of a limiting reactant. You have many slices of bread, I don't know how many, a bunch of them, and you only have 3 slices of ham. If you're making ham sandwiches, then you're able to only form, or to only make 3 sandwiches, because you're limited by this, not by this. So that means that you're going to have leftover of your bread, and your ham is going to be completely used up. So after you make that 3rd sandwich, you're pretty much done. That is what it means to be a limiting reactant. It's exactly what happens. Instead of bread and ham, we're dealing with molecules. But we're always looking for the one that gets used up first, and that is the one that will tell me how much can I actually make. So just by looking at this picture, I can tell you that I cannot make more than 3 sandwiches because of the ham right here. And that is what the limiting reactant, why is important. So for instance here, we have a 2-to-1 ratio between hydrogen and oxygen to form 2 molecules of water, right? And we have 2 molecules of hydrogen as the original quantity, oxygen as my unknown. I don't know how much unknown I'm using. So if I have, let's say, 2 molecules of this, actually we have them here in the little drawing. So if I have 4, the white ones are my hydrogens, so 4 of these, how many oxygens am I going to need? Well, for that, I need to look at the mole ratio. I have 2 molecules to 1 or 1 to 2, whichever one works out best. In this case, the right one is the one that I want because I'm looking for how many oxygen molecules I need. 4 molecules of hydrogen, and this should be, that one shouldn't be there. So let me just, no. 2 hydrogens for every 1 oxygen forms 2 water molecules, which is what we have right here. Now, there's 2 possible outcomes whenever you're trying to determine the amount of product that you can form. If you have more than 1 reactant, then one of them is going to be the limiting reactant. The other one is going to be what we call the excess reactant. What determines which is which? Well, you can calculate how much of the product you can obtain with either one of them, and the one that gives you the least amount of product, that is going to be your limiting reactant, because it's the one that's going to get used up first, just like the hams and the bread. So for instance here, in this drawing that we have right here, we have 4 molecules of hydrogen, 3 of oxygen. So for every 2 of oxygen, I use 4 of hydrogen right here, and I form 4 of water. But that means that the 3rd molecule of oxygen is not going to get used. It's just going to hang around. It's not doing anything. Literally, it doesn't do anything. So we call that the excess reactant. The hydrogen, on the other hand, gets used up completely, so it becomes the limiting reactant. And then the product is just a product. It doesn't take part in this because what we are trying to look for here is how much of my reactants I need in order to form a set amount of product. This is very important, especially in industry, because you want your limiting reactant to be your more expensive reactant or your more difficult to obtain reactant, and then the one that you can literally obtain in big amounts, and then that's going to be your excess, or the cheapest one is going to be the one in excess. And that's one of the many applications that this type of analysis gives us. So here, for instance, using the balanced chemical equation, which we always need to work with a balanced chemical equation, determine the limiting reactant when we have 10 grams of my nitrogen and 10 grams of my oxygen to form however much of my nitrogen monoxide I'm forming. So I have starting quantities, but I can't compare grams to grams. I never could, and I never can, and never will be able to. But I can compare moles to moles. So my first step will be changing all of those grams into moles. So I grab the molar mass for nitrogen and oxygen, which again is in the periodic table. So 2 times the number right below that N gives me the mass for the nitrogen molecule, and then the same for oxygen. This is the number of moles that I form for nitrogen and for oxygen. Now I'm going to take a step back. For every 1 mole of nitrogen that reacts, I will need 1 mole of oxygen. So that means that if I have 0.313, I will need 0.313 of my nitrogen. As you can see, we have more nitrogen than we do oxygen. So I can tell you right now that this right here is going to be my limiting reactant. Now, that is pretty much what they're asking us for. And as you can see, we actually have it here. And that's pretty much it. You just analyze which one of them gets used up first. That is your limiting. The other one is your excess reagent.